So we will now talk about the core objects of this chapter, namely C0 semigroups. So we were looking at V Banach, A in LV, bounded linear operators, continuous linear operator, and then we were looking at S of t equals e power ta. So which is a group of operators. So okay. So now we want to imitate the properties of this in an abstract sense. So we start with the following definition. So V Banach space and S of t greater or equal to 0, a family of continuous linear operators. On V. It is said to be to form a C0 semigroup if the following hold. One, S of 0 equals identity, so identity in V. Okay. 2, S of t plus t dash equals st dash for all t dash greater or equal to 0, and then 3, for every u in V you have limit t decreasing to 0 st of u equal to u. So if these three properties are satisfied, then you have what is called a C0 semigroup. So remark, 2 is called semigroup property. And if it is a group, if this is true for all t in R, if true for all t in R, then you have t dash in R, then we have a group and you have st inverse is S of minus t. Okay, st will be invertible and its inverse will be S of minus t. Now C0 refers to property 3, namely you have some kind of continuity at the limit at t equal to 0. Okay. So examples of example 1. So A in LV, bounded continuous linear operator, then you have st equals e power ta is a C0 semigroup. I put semi within brackets because it is in fact a group in this case. Okay, so now we will look at a genuine another example, example 2. So V equals bounded uniformly continuous operators functions on R. So bounded uniformly continuous functions R to R, okay, with the sup norm. So this is a Banach space, as you probably know, otherwise you can check it. And then for F in V, so we define st of F. So this must again be a member of V. So if you put it as S, then this will be F of t plus S. Okay, so this is for all t greater or equal to 0, S in R. Okay, then of course S of 0 is identity, that is obvious because S of Ft is nothing but F of S again. And then the semigroup property is obvious because if you translate once and then you translate by another number, it is the same as translating by T1 plus T2. okay, and then the continuity comes because you have, they are all uniformly continuous functions. Therefore, given any epsilon positive, there exists a delta positive such that f of t plus h minus f of t is less than epsilon for all t in R, okay, or if, maybe I should put f of s plus h minus f of s, okay, and therefore mod s h of f minus f 0 infinity R is less than epsilon, and therefore you have that sh of f goes to f as, so sh of f goes to f in V as h goes to 0. So, this is an example of a C0 semigroup. So, now let us quickly start various properties of the semigroups. So, theorem 1, V Banach and ST t greater or equal to 0, a C0 semigroup on V. Then there exists m greater or equal to 1 and omega in R such that norm of ST is less than or equal to m times e power omega t for all t greater or equal to 0. Okay, so proof. So, there exists an m greater or equal to 1 and delta positive such that for all 0 less than or equal to t less than or equal to delta, we have norm of ST is less than or equal to m. So, if not, so m can be taken bigger than 1 without loss of generality. Okay, so you have a constant m, and then now if not, there exists a Tn decreasing to 0 such that norm of Stn is unbounded. But Stn u goes to u for every u in V, that is property 3, and therefore by the Banach-Steinhaus. So, so this contradicts Banach-Steinhaus. So, it is pointwise bounded, so it has to be uniformly bounded. So, it goes converges for every u, and therefore it is pointwise bounded, but then Stn is not uniformly bounded, and this contradicts. Therefore, there exists an m which you can take bigger than or equal to m. Okay, so now you define omega. So, define delta inverse log m, which is positive. Okay. Then given any t greater than or equal to 0, there exists an n in n and eta such that 0 less than eta less than delta such that t equals n delta plus eta. So, what you are doing is you are taking, you have t here, you have 0 here. So, you go by steps of delta till you come near it, and then t will be finally n delta and then plus n eta. Okay, so, you go n steps and then you get here. So, therefore, you have S of t by the semigroup property. This is nothing but S delta power n times S eta. So, norm of St is less than or equal to norm of S delta power n times norm of S eta, which is less than or equal to m power n times m, and now you have log of m power n equals n log m which is equal to n omega delta, and that is less than equal to, since n delta is less than t, you have this is less than equal to omega t. Okay. So, this is less than equal to log m power n is less than equal to omega t. So, m power n is less than e power omega t times n. Okay. So, therefore, this proves the theorem. Corollary. So, for every u in V, you have t going to st of u is continuous from 0 infinity into V. Okay. So, proof. So, let h be greater or equal to 0, norm of s of t plus h u minus st of u is less than equal to norm of st using the semigroup property always into norm of sh of u minus u, and that is equal to m times e power omega t times norm of shu minus u, and this goes to 0 as h goes to 0. Similarly, norm of st of u minus s t minus h u is less than equal to norm of s t minus h times norm shu minus u, and that is less than to m e power omega times t minus h times norm shu minus u, and again that goes to 0 as h goes to 0. Okay. So, this proves that implies t going to st of u continuous for every u in V. Okay. So, we say, we symbolically write this. So, remark, the statement of the above theorem above corollary rather is written as S dot u belongs to C of 0 infinity with values in V. Okay. So, it is a Banach space continuous function from for every t, that means t going to stu for every u in V. Okay. So, this is the statement which we have there. So, definition, if m equals 1 and omega equal to 0, then norm of st will be less than equal to 1 for all t. So, this is called a semigroup of contractions or a contraction semigroup. Okay. If norm of st is less than equal to m times e power minus omega t for omega greater than 0, then we say that is also possible. I mean, we showed that it is less than m e power omega t, that is a general number which we have got, but in reality it can happen that can also be less than this, and then we say that st is exponentially stable. So, example, if A is a n by n matrix, all of whose eigenvalues are of negative real part, then e power t a is exponentially stable. We can prove this. I am just stating it now, but we'll probably see it in the exercises or in the assignments. Okay. So, since you have the t going to st of u is continuous from 0 infinity into v, therefore, we can integrate the a continuous function with values in a Banach space. Okay. So, lemma, let u belong to v, then limit h decreasing to 0, 1 by h integral t to t plus h, s tau of u d tau is nothing but st of u, the lower end, the value at the lower end. Okay. So, proof. So, let epsilon be greater than 0 be given. So, 1 by h integral of t to t plus h, s tau of u d tau minus st of u can now be, then this is a constant, so I can pull it into the integral. So, this is 1 by h norm of integral t to t plus h of s tau minus st of u d tau. And from the properties of the integral, this is less than 1 by t, 1 by h integral t to t plus h norm of s tau minus st u norm u into d tau. Or rather, let me not write it that way. So, s tau of u minus st of u d tau. Okay. But you know that t going to st of u or tau going to s tau of u is continuous. Therefore, there exists a delta such that for all mod h less than delta, we have or rather if tau minus t less than delta, we have norm of s tau of u minus st of u is less than epsilon. That is just the definition of continuity, and therefore you have that this thing is less than epsilon, and therefore you have for all mod h less than delta. Okay. So, this proves the theorem. So, now we are going to introduce a very important concept. Okay. So, definition. So, V Banach ST t greater or equal to 0, a C0 semigroup. The infinitesimal generator A of ST is defined as follows. So, D of A, the domain of A, it is an unbounded operator which we will see. So, this is set of all u in V such that limit h tending to 0 st of u minus u by h exists. And if u is in D of A, we have au is the limit of h tending to 0 st of u sh sorry h of u minus u by h. Okay, so this is the definition of the infinitesimal generator, which will play a very key role in the theory. So, a very important definition. Okay, so example 1. So, you have A in L of V, bounded linear operator, and you have ST equals e power Ta. Then we have seen limit h going to 0 e power ha u minus u by h equals AU. We did this computation yesterday, and therefore we have that A is the infinitesimal generator. So this is true for all u in B, okay, of e power ta, and in fact it is a bounded linear operator, okay. So in this case it is not just an unbounded, it is defined everywhere. So now let us look at the other example. So let V as usual bounded uniformly continuous functions on R, and ST f at S is f of t plus s, the translation semigroup, okay. So you translate by t is the semigroup. So then suppose f belongs to D of A, that means limit of h going to 0 sh of f minus f at S by h should exist, and this, but we know if the limit exists, this is d plus f of S, the derivative, one sided derivative, and so d plus of f of S exists for all S, and you have d plus of f belongs to BUC. It is a bounded uniformly continuous function because we know that the limit should now you look at f of S minus f of S minus h by h. This you can write as d plus of S minus h of d plus f at S minus h plus little o of h by h. By this, by little o we mean that the numerator goes to 0, this quotient goes to 0 as h goes to 0, okay. So little o of h by h, okay, and so as h goes to 0, this will converge to d plus f at S, because d plus f is a continuous, in fact bounded uniformly continuous, and this part has to go to 0. So that means d minus f s exists for all s, and d minus f s equals d plus f s. Therefore, that is, if f belongs to the domain of the infinitesimal generator, then we have that f is differentiable at all points, and f dash belongs to BUC, and you have A of f is nothing but f dash, okay. So this is the not it, sorry. So yeah, in fact, okay, AF equals f dash, okay. So conversely, assume f belongs to BUC of R such that f dash is also in BUC of R, okay. Then we claim f is in dA and AF equals f dash. So for that we denote phi h of S is f of S plus h minus f of S by h, okay. Now f dash belongs to V, which is BUC of R, bounded uniformly continuous functions in R, and therefore phi h of S minus f dash of S equals 1 by h integral S to S plus H of f dash tau d tau, that is just fundamental theorem of calculus, minus f dash of s, and that is equal to 1 by h, again integral s to s plus h f dash of tau minus f dash of s d tau, because f dash s is a constant as far as this integration is concerned. Now, if you have epsilon greater than 0, by uniform continuity of f dash, there exists a delta positive such that mod tau minus s less than delta implies mod f dash tau minus f dash s is less than epsilon. This is uniform continuity, and therefore this means that if h is less than delta, we have phi h of s minus f dash of s in modulus is less than or equal to 1 by h f dash tau minus f dash s is less than epsilon. You pull it out and then you have integral s to s plus h tau d tau by h. So, the whole thing is less than epsilon, okay, for all s. That means phi h converges to f dash uniformly, okay. That means but that is exactly saying that is f belongs to d of a and a dash a of f equals f dash. Therefore, you have that d of a equals set of all f in BUCR such that f dash belongs to BUCR and a of f equals f dash. So, this is the infinitesimal generator in this case. We will see a lot more about infinitesimal generators subsequently, and we will investigate the properties of the infinitesimal generator next.